Good afternoon, welcome back. Session 5 starts now. I hope you guys learned a lot in session 4, but we're going to build on it some more this week. Last week I think we talked a lot about probability distributions, continuous, discrete, both of those, normal distributions. We talked about that and all the different ways that we can use those z-scores to find probabilities underneath that bell curve. So this week we're going to be talking about what's called a sampling distribution, okay? And so kind of what those are is basically you have your whole population, right? You have your population distribution, and you basically take a small sample from that population distribution, and you turn it into a sample, right? So we have that. So we then have a sampling distribution. Okay. These first couple slides are just really like a bunch of key terms to know, so that way whenever we do talk more in depth on these, if I say if I say a term, it's not going to be lost on you guys. So that's really what these first couple slides are about, right? So we have our sample statistic. We probably talked a lot about these in the first chapter when defining statistics, but this is just a variable whose value depends on which population items happen to be in the sample, right? So if I want to find the mean of a sample, it depends, or that mean is going to depend on the items that I take in that sample, okay? Standard deviation, right? That's going to depend on the values that I take in that sample. Again, a sample could represent the population well. It also couldn't, especially if the sample size is small, right? We never want to take we can, but we never want to take a small sample size. Okay, we want to always represent our data well and accurately. So, and these sampling distributions just describe the behavior of the sample mean, other statistical estimators. We'll talk about estimators in the next couple slides, but we talked about population parameters, right? We know what parameters are. They're just the statistical explanatory variables that go along with the population, right? And it can explain how to make inferences about the population, and it takes into account these four main factors here. And I put the ones that are uncontrollable, the ones we have no control of, and the ones we do have control of when taking these sampling distributions, right? So we have our variation, our sampling variation, that's uncontrollable, how far away the data is from the mean, all that stuff. Population variation, again, that's uncontrollable. If you have a population, those data values, you can't control that, okay? But you can control your sample size, right? If your sampling distribution, you can pick your sample size, right? And we'll get more into that. In terms of finding probability and all that stuff, right? There's an easy way to find probabilities for sampling distributions, right? We talked a little bit about it last chapter, and we'll get more into it this chapter, okay? And then just your desired confidence in the estimate. We can control that, right? Any good outfit you wear, the key thing is, even if it doesn't look great, if you have confidence in it, you can rock it. There you go. A little confidence for you. Anyway, estimator. We talked about this in the last slide, but estimator, it's just a statistic derived from a sample to infer the value of a population parameter, okay? A sample mean, sample variance, sample standard deviation, all that stuff, those are sample estimators, okay? Again, estimate, just the value of an estimator in a particular sample, right? So, again, just to kind of differentiate between population and sample, our population parameters are always denoted with a Greek letter, right? Mean is mu. Standard deviation, sigma. This is pi, right? Pi, we talked about binomial distributions. Pi is always the chance of success, right? So we denote the population with Greek letters a lot of times. And then for our sample estimator, obviously we use a Roman letter, which is like you can do X bar, which is the sample mean, S, which is the standard deviation, P, which is, again, you can say the Greek letter pi, right? It starts with a P, so you can just say P, just the chance of success, okay? So this is just kind of how you differentiate between population and sample, and that way you can kind of, know how to use it without having to guess. Again, sampling error, right? So when we take a sample, the main thing we can kind of run into, especially for small sample sizes and stuff like that, is sampling error, okay? And so all it is just you take your sample mean and you subtract it from the population mean, right? And that's how you kind of get how much sampling error you have in that in that one specific sample, right? And again, these are just a lot of different key terms to know, so that when we go into this more later, we can not be completely ignorant to all of the different things that we're talking about. So bias, which is another thing that we can have in sampling, right? Again, we always have that unconscious bias that we do, or that we have when taking samples, right? So there's bias involved. And again, this is just the expected value of the mean, right? It's just the same, kind of the same thing. And then the true parameter, right? So the expected value of X bar, the expected value of the mean, minus the true mean, right? The true population mean, population parameter, okay? Again, an estimator is unbiased if its expected value is the parameter being tested, right? So if your expected value is the population mean, you're gonna have zero bias in that, okay? It's just one of those things. And a lot of times the mean, or the expected value of the mean is always an unbiased estimator. So a lot of times we can use that as our unbiased. I think also standard deviation's one, stuff like that. So, and again, unless we know the population parameter, we can't know the sampling error or bias. That's just one of those things, right? Obviously, if we don't have our population mean, there's no way we can find our sampling error or our bias. So, and if we knew the population mean and standard deviation and stuff like that, we wouldn't even need to take a sample. Okay, so you wouldn't need to take a sample, but if you wanted to, just to kind of knock down your numbers, you can. Okay, that's just kind of some little thing to know. Again, talk about efficiency when doing samples, right? We always want to be efficient. You can kind of think about like when you're at a shooting range and you're shooting at a target, right? You want to be as efficient as possible. So like a good thing when you're shooting a weapon in the shooting range, right? If that sight's not scoped in correctly, no matter how good of a rifleman you are, let's say there's the best one to ever shoot a rifle, okay? If that sight's not scoped correctly, it's not gonna be as efficient, right? It's not gonna be as you're not gonna get an unbiased sample. I guess that's a good way to say it. If it's scoped correctly, you're gonna have your target, and it's gonna be centered right here. A lot of times, you may have a little bit of spread, right? But more times it's gonna be hitting that center, right? But if it's not as efficient, if it's scoped incorrectly, you may have your target here, but it's gonna be shot over here. It's gonna have the same spread. It's just gonna get shot maybe to the right or the left, right? So that's how we want to be efficient. Okay, consistency. Again, that deals with the spread of the data, right? Again, shooting a target, the smaller spread you have, so the closer the shots are together, the more consistent you are, right? This further the spread, the less consistent it is, right? Just a good way to think about it, okay? Again, and a consistent estimator always converges towards the parameter, right? So the bigger the sample, hopefully the more it converges towards that population parameter that's being estimated, right? As the sample size increases. So that's just two more things to kind of think about when taking the sampling distributions. And here I just wanted to kind of give some like example estimators, right? Like what the heck are we talking about? Again, 3 kind of important estimators, right? We have our sample mean, our sample proportion, and our sample standard deviation, okay? And again, these are all parameters, mu, pi, sigma, all those things. That's how we kind of, differentiate between the population and the sample, right? So this is our sample mean, sample proportion, sample standard deviation, right? We all know the formulas for all of them. We've done them 100 times, okay? These are just some examples of our estimators. So in these sampling distributions, all these really are, again, we talked about distribution, all that stuff. It's just assigning probabilities to all the possible values a statistic may assume when a random sample is taken of size whatever, okay? Again, we just assign probabilities to them. That's all it is, right? And then the sample mean, X bar, of course, it's used to estimate the population mean, right? So our objective, again, is to use that sampling distribution of whatever our sample mean is, taking in objects, adding them all together, dividing by the number, and then we take that X bar and it helps us say something about the population we're studying. And hopefully our sample is accurate enough and efficient enough that we can get a good, solid representation of our population, okay? And again, to describe the sampling distribution, we need to know the mean, variance, and the shape of the distribution. Okay, those are the three main things we gotta know. We've already learned this, right? The expected value of X bar is always our mean, right? Expected, again, we call it the expected value of the mean. Okay, again, we know X bar, it's a random variable. It's gonna change whenever we change the sample. So if we take a different sample, X bar should hopefully change. If not, I don't know, you just got lucky, I guess. But again, as long as our samples are random samples, and we talked about that in the first chapter a long time ago, the only error we can really run into is sampling error. And again, that falls on us as the statistician to take accurate samples, excuse me. Or else, again, we can run into that sampling error. So the sampling error is described by its standard deviation, right? It has a special name. We just call it the standard error of the mean. And we denote it here as the sigma of, I think it says sigma of X here, but it could be any X. It's not like a specific value, it's just any X, okay? That's all I mean by that. And so this is the formula for our standard error. Again, don't get this confused. Anytime you see sigma of X, don't get that confused with standard deviation, okay? Because this is our standard deviation here. That's how we find the standard error. This is the standard error, okay? So again, we just take our standard deviation, we divide it by the square root of our sample, okay? And again, I hope you notice as n increases, our standard error should decrease because this n is getting large, right? If I take the square root of 2, or square root of 4, excuse me, that's 2, right? Anything divided by 2, it's kind of a big number, right? If I take the square root of 16, that's 4. That bottom number gets bigger. Anytime I divide by a larger number, that number should shrink, okay? Think about it that way. For example, this is just a for example, okay? We have the average price of a 2 terabyte. This is a terabyte external hard drive, right? So how do we store our data on hard drives? This is an external hard drive. A lot of computers have, you know, I don't know, Mrs. Bernardi, for instance, I know she has a lot of stuff on her computer. She has to probably have an external hard drive to store all of the other stuff on her, you know, that way she doesn't overload her computer and she can't save anything. So she probably has 400 of these. But anyway, we have our average price of a 2 terabyte external hard drive, our population mean, right, of $150, and it has a standard deviation, a population standard deviation equal to $20, okay? What will the mean and standard error of X bar from a sample of 20 hard drives be, okay? So in this case, again, this is our expected value of the mean, right? We just take it and we'd say it's $150 of our sample, okay? Because we're assuming a normal, because we're assuming a normal distribution here, we can take it as the mean, the expected value. Well, I guess actually, since we already learned this, the expected value of the X bar of our sample is always equal to our population mean. That's why we could do this. There you go. I figured it out. Critical thinking. Okay, our standard error. Again, we just use the formula that we talked about in the last slide. We take our standard deviation, we divide it by the square root of our sample size. So it's, in this case, the square root of 20. We get 4.472. I know you can't have 0.472 cents. This is just for accuracy's sake. I thought about rounding down, but then I was like, well, it's only 3 decimal places. We'll be fine. So anyway, this is our standard error, okay? Not bad. Again, if the population is normal, then the sample mean follows a normal distribution for any sample size. Again, we'll get more into that in depth in a little bit. But again, for these sampling distributions, here's the key. Here's the thing I want you guys to know. Look at me. Pay attention. Anybody who's not paying attention, get off your phones. In sampling distribution, the way we can find probability and do all these things is you want to take a sample, and these sampling distributions, you want to always make sure that you can get them to a normal distribution, because once you get them to a normal distribution, we can then find the z-score based on that pretty little appendices that we talked about last chapter, right? C-1 and C-2. That makes it so much easier to find these probabilities if we can assume a normal distribution for the sample, okay? That's literally all this chapter is about, sampling distributions, right? How we can get them to be normal, how we can assume normality, so that way we can easily find probabilities. That's what this whole chapter is about. So if you don't take anything else from this, just remember, anytime we take a sample distribution, we want to make sure we can assume its normal, we can assume its normality, okay? We can assume a normal distribution that helps us find the probabilities easier. That's what this chapter is about. Okay. So if population is not normal, or we don't know the population distribution or what it looks like, we can use one of the fundamental laws of statistics. This is a big one, okay? It's called the central limit theorem, all right? And there's three main points here that we can talk about in the central limit theorem, okay? And it's just a powerful result that allows us to approximate the shape of a sampling distribution, okay? Of X bar, even if we don't know what the population looks like, right? So if the population distribution is skewed left, skewed right, symmetric, we may not know, but it allows us to assume or approximate the shape of our sample distribution because of this theorem, right? So here's the three important facts to know about this thing here, okay? If the population is normal, sample mean has a normal distribution centered at the population mean, and it's equal to, or the standard error is equal to, again, our function that our formula that we talked about earlier, okay? That's if we already know the population is normal, okay? And as sample size n increases, distribution of the sample means converge to the population mean. And I'll talk more about this. It'll make more sense as we kind of get visually what it kind of looks like. But just imagine as your sample size increases, all those sample means from your population always converge to the true mean. Okay, that's all that's saying. And again, even if your population is not normal, by this theorem here, if the sample size is large enough, and we'll talk about what is large enough here in a second, the sample means will have approximately a normal distribution. Okay, so if the sample size is big enough, we can always assume approximately a normal distribution that allows us to use those normal z values or normal standardized values. Okay, that's what the central limit theorem is all about, right? Assuming normality based on the sample size, and it just allows us to easily calculate the mean and the standard error of our sample. Okay, so again, the central limit theorem applies to sampling distributions from any population, right? So the population could be a normal distribution, could be a uniform distribution, a skewed, or just some weird general distribution, okay? So what it's saying is, here's our population distribution, right? As n increases, we can kind of get to a better, as n increases, we always, those sample means always converge to our true mean, to our true population mean, and we can then assume a normal distribution for any sample, okay? And usually for these kinds of, usually especially for if you're, for these kind of population distributions, any sample size greater than 30, we can pretty much assume a normal distribution for that sample, okay? That's usually the rule of thumb. There's obviously always an exception to the rule, but in 90 to 95% of the time, if your sample size is greater than, actually 100% of the time, if your sample size is greater than 30, we can assume, a normal approximation, a normal distribution for our sample, okay? And that's for any population distribution, normal, uniform, skewed, or otherwise, okay? That's really just what this is saying, okay? Again, we have those three facts here: converging, 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 and then of course we get to n equals 30, we have all of these normal distributions here. So, application of the central limit theorem. You're like, okay, well, this is cool and all, but what the heck does it mean for me? Okay, let's just talk about gas for a second. I know this problem was probably made, I don't know, 100 years ago when gas was cheap, but bear with me here, okay? During a certain week, the mean price of gasoline in California was $1.16, let's just say 16 cents here, just for the sake of the problem, but it's 164, okay? This is our population mean, right? The mean of all of the gas prices in California, which would take a long time to calculate. You don't have to. Okay, it's asking what is the probability that the mean price for the sample of 38 gas stations in California is between this number and this number, right? And then of course it gives us, assume our standard deviation. So it gives us our population mean and our population standard deviation, right? And of course, since n is greater than 30, right? We have our 38 sample here. Since n is greater than 30, our sampling distribution of x bar will be normal. We can assume a normal distribution. Okay, again, thanks to our central limit theorem. Okay, so we can find, again, mean of our sample mean. Our sample mean is obviously equal to, or I guess our expected value of the mean, that's what this would be, is equal to our population mean because it's a normal distribution, right? So it's equal to our population mean, our standard deviation. In this case, since it's a sample, our standard error of the mean. We can use this formula here. So we have 0.049 divided by the square root of our sample size. We get this number. This is our standard error of our sample, okay, or of our mean. So we have everything we need here to find the z-score, right? We know the formula for z-score like it's, you know, imprinted or tattooed on the back of our brain, right? It's our z equals our sample mean, right? So our sample mean, our sample value that we're trying to, you know, or that we figured out here, or I'm sorry, that we figured out here, right? Sorry, let's just back up. We have it's our x value, right? What we're trying to find. So in this case, we have two of them. We have this one and this one. So we have to find two different z-scores, right? So in this case, we have 1.169 minus our sample mean, our sample mean, which of course is our population mean. But since we're trying to find the z-score of the sample, we have to take our sample mean, and then we divide it by our standard error, right? And we do that for both scores. And again, since these are normal, we can go back to our appendices C-1, C-2. In this case, it looks like it's a middle area, right? And I think we talked about this in the last chapter. If it's a middle area, it'd be easier just to find use appendices C-1, I believe, because it's everything from 0 to the right. Yeah, 0 to the right or 0 to the left. 0 to the z value, let's just say that. 0 to the z value, right? So you can do 0 to 1.90, 0 to 0.63, and then you can subtract them because again, you don't want to calculate these probabilities twice because they overlap each other, right? So you subtract them, then you find your probability, and that is your probability that the gas prices of these 38 gas stations is between this number and this number, okay? I know that was a lot of words, a lot of talking, but I hope this makes sense to you guys, okay? We always want to get it to a normal distribution. If we can do that, it makes our lives a lot easier, okay? Again, here's another example. I'm sorry this is cut off, okay? This was in a YouTube video. If you want to find the YouTube video, I'll attach the link to it. But I was told you guys didn't really like the video in the last video. So I'm going to talk about it a little bit quicker than probably what they would. So you're welcome. But I'll attach the link if you want to, slow it down and make some more sense, okay? He'll explain it a little bit better than I would. But anyway, so the last example we did was dealing with sample mean. And in this one we deal with sample proportion, okay? A sampling distribution based on a proportion, okay? And so again, it says that suppose that 15% of the 1,750 students at a school have experienced extreme levels of stress. I'm sure that 100% of you are feeling that way right now, just reading this problem, okay? During the past month, I'm sure for you it's probably been the past day. A high school newspaper doesn't know this figure, but they are curious this is all cut off, but what the proportion is, I guess. So they decided to ask a simple random sample of 160 students. Again, what I would do when reading this problem is I would label everything as I read it, right? So we have our population proportion, our population size, right? We have our sample size, and it says they asked a simple random sample of 160 students if they have experienced extreme levels of stress during the past month. And subsequently, they find that 10% of the sample replied yes to the question. So out of 160 students, 10% of the sample replied yes to having high levels of stress within the past month, okay? So our question is, and again, this is our sample, I guess you could call it our sample, well actually no, It's actually the probability. So anyway, just bear with me, okay? So our question is, assuming our true proportion is 15%, so our population proportion is 15%, what is the approximate probability that more than 10%, I know it says 0 here, but it got cut off. What is the probability that more than 10% of the sample would report that they experienced extreme levels of stress during the past month? Wordy, I know, but we're gonna get through it, okay? I've given you everything you need to know here, all right? And again, I cut this off because I couldn't fit it in the video, but imagine a bell-shaped curve here. We have our population mean, or our sample mean, excuse me. We have our sample mean in the middle of the bell-shaped curve, and what this is asking is what is the approximate population that our proportion is, or what is everything that's greater than 10% of our sample, right? So what's the probability that more than 10% of our sample experiences high levels of stress within the past month, right? That's what this is asking, okay? And again, the video, you'll be able to see it step by step, and it'll make a lot more sense. But for these kinds of proportions, right, for the sample of the mean, we just said if the n's greater than 30, then we're good to go. We can, hey, we're good. We can assume normality. For proportion, it's important to realize there's two main rules that we have to follow to assume normal, okay? And in this case, it's this rule and this rule, right? So we have our sample size times our proportion, and it has to be greater than or equal to 10. And we have our sample size, and we have to do 1 minus p. So, right, so think about it this way. I have to do sample size times the chance of success, right? We did this in normal approximations of binomials, the same two rules. We have n times the chance of success, and we have n times the chance of failure, right? So n times p, n times 1 minus p. If both of those are greater than 10, we can assume normality, we can assume it's a normal distribution, and then we can use our standardized z-scores, okay? Again, 160 times 0.15, greater than 10, obviously. 160 times 0.85, really greater than 10. So we can assume normality. We can assume a normal distribution. We're good to go, okay? So we have our sample mean. Again, since it's normal, we can just take it as our population proportion, 0.15. And then, our standard error of a proportion is a little bit different from the standard error of a sample mean, right? So in this case, it'd be the square root of p times 1 minus p divided by n. Okay, so find these numbers divided by n and then take the square root, right? So 0.15 times 0.85 over 160, square root that, and we get approximately 0.028, okay? So now we have our sample mean, we have our sample standard error of our proportion, okay? And now we can find our z-score, okay? And I think once you work this out mathematically, you find your z-score, and then you can take everything. Again, I would use appendices C-2 here. So that way because again, C-2 is everything from the z-score and then to the left, right? So everything from here to the left. Since we're trying to find everything to the right, all you have to do is find that z-score and you subtract 1 minus that probability. You'd get everything to the right of that z-score, okay? That's what I would do personally. And I think once you calculate all of that, you get approximately, I think I got approximately 0.96. I think that's the answer to that. And again, it's in the video. I'll attach the link to this. You'll be good, okay? But another way to use our sample distributions to find probability, right? We've done probability all of last chapter, and we'll continue to do it for this chapter as well, okay? So anyway, that's just a couple applications of sample distributions, but in this one, we're going to talk about, again, all coming back to the CLT or the central limit theorem. We can have a range of sample means, right? So it permits a range, or an interval within which the sample means are expected to fall, right? So again, like I can say with 90% certainty that our sample means will fall in between this number and this number, basically what it means, right? So again, we have to use, if we know the population mean and the standard deviation, the range of sample means for sample size n are predicted to be, and again, these are 3 different values, right? Again, 90%, this is the z-score for 90%, right? We're just taking the z-scores of these different population, or the different probabilities, right? So 95%, we find the z-score is 1.96. Again, it may be useful to write some of these down so that way you don't have to find them every time in the appendix, okay? So, just a little hint for you, because you do have note cards. You will have a note card for the final. I know this will be on the final. Maybe, maybe not. Okay, write these down. It's important. Okay, 99% interval, we have a z-score of 2.576, all right? So again, as you can kind of see, our sample means here, we just take the mean and we plus minus it, right? So we have to add, and then we also have to subtract to get our interval, right? So we just take basically the z-score times the standard error of our sample, okay? That's all this is saying, right? So then we have our interval for which these sample means may lie, all right? So for example, within what interval will we expect GMAT sample means? So GMAT is just, it's an acronym for Graduate Management Admissions Test, right? And so this is the test you take if you want to get an MBA, Master's in Business Administration. That is the test you would take if you wanted to get into a master's degree for that business administration. I didn't have to take it for my master's in analytics, so I didn't have to take this. I highly encourage you, if you do want to further your education, a master's in business administration would be really good. So there you go. Anyway, within what interval will we expect the sample means from those tests to fall for a sample of 5 applicants, right? And again, it gives us our population, or it tells us our population is approximately normal, and it gives us our parameters mean, 520.78, and our standard deviation, 86.80, okay? And again, I gave you these intervals here just so that way you can kind of constantly refer back to them, right? Because eventually I hope you guys will just like know, oh, 90%, 1.645, right? That's the z-score. I hope you guys get there. If not, that's okay. But anyway, use this formula. So using the formula, we can get the range of, again, this is, we're using a 0.9, or I'm sorry, I should have designated what interval I wanted you to check, but I meant to say 95% interval. Oops, my mistake. Teacher messes up, that's fine. Okay, we all make mistakes. But anyway, we're trying to find the 95% interval, so we take this formula here, we do mean minus the standard error times the z-score, and then the mean plus the standard error times the z-score, okay? And we get this range, so all that's saying is, this is the predicted range for 95% of the sample means, right? So 95% of the time, we take a sample, and our sample mean will fall within that range. Again, 95% of the time. That means 5% of the time, it won't, okay? And that's okay. That just means that for that specific sample, it didn't fall within that 95% range. And again, I guess I just want to say this. You can take a 99% interval, and some would think that that would be a better estimate of our sample. But think about it this way. You're multiplying by 1.96 here. You're multiplying by 2.576 here. You're multiplying by a bigger number. You may think it's a better estimate, but that 99% interval is just going to have a wider. It's just going to have a wider interval. So in this case, it's really not a better estimate of your data. Okay. So I just wanted to clarify that real quick, so that way if you do like, oh, I'll just take a higher interval, you can, or a higher confidence interval, or a higher 99% interval, right? You can, but you'll have a wider range of values to pick from. So be cautious of that. Okay, so now I'm gonna give you some problems to think about, okay? I actually didn't add this problem in until late, and I didn't think about adding it until just now. But there's an additional problem in here for you that's gonna make you think a little bit, and I hope it does. I want you guys to talk about it, think about it, and see if you guys can figure it out, okay? And it's 8.3 in the textbook, right? So if you have the textbook, it's problem 8.3. Again, it's probably gonna be in chapter 8, if you hadn't figured out already how the problems work. But so just do it between 8.1 and 8.4. Talk about it, think about it, and then we'll get back to the video after this. See you guys in a second. Okay, so we talked about sample ranges for sample means. Now we're going to talk about a confidence interval. And again, this is just for the population proportion, right? There's confidence intervals. You know, we did an example for sampling distributions for population proportions. We did sampling distributions for the sample mean. In this case, really briefly, we're just going to talk about confidence interval for population proportion, okay? And we'll get into confidence interval for sample means in the next video, okay? But in this case, all a confidence interval is just a range of values we're fairly sure our true value lies in, okay? So again, we did our range of sample means in the last section. This one is just a confidence interval for how sure we are that the true mean, the population parameter that or the true value, the population parameter that we're researching, how confident we are that it lies within that range. Okay, that's all that this is saying, right? So just kind of flip it on the other. It's like a swap, if you will. Okay, so based on our knowledge of the sampling distribution of X bar, we can create an interval estimate, and then we can create a confidence interval for the unknown population proportion by adding and subtracting a margin of error from X bar. And we'll get into all of that here in a second, okay? But it's really simple. I really broke this down for you, so if you don't really understand it yet, that's fine, okay? And again, we can have our confidence interval. It's expressed as a percentage, just like the range of sample means, right? We have 90, 95, 99, all that, etc., 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 okay? So, you find the confidence interval, call it CI, okay? For a population proportion to show the statistical probability that a characteristic is likely to occur within the population, okay? A lot of times we deal with population or confidence intervals for these kind of proportions when the category or when the characteristic is being measured is categorical, right? That's when we deal with these kind of population proportions, right? So for example, like opinion on an issue, support, oppose, are we neutral about it? Gender, male, female, political party, Democratic, Republic, Independent, type of behavior, do or don't wear a seatbelt while driving. I hope all of you do. That's safety. Okay. Most people want to estimate the proportion or percentage of people in the population that fall into a certain category of interest. That's what these proportions deal with. Okay. For example, we consider the percentage of people in favor of a 4-day work week. Me. The percentage of Republicans who voted in the last election. I don't know. I don't talk politics, but proportion of drivers who don't wear seatbelts. I hope all of you do. Again, safety. In each of these cases, the object is to estimate a population proportion P, right, or pi. I guess in this case would be our population proportion. Again, we can also use if we use P as our population proportion, we also can write what's called a P hat, right? It's just a P and then it has like a little hat on it, and I'll show you that in the next slide. But P and P hat, as we call it. So using a sample proportion plus or minus a margin of error, this result is called a confidence interval for the population proportion P. Okay, so right, we have our population proportion P. P hat is literally just this P and has a little what looks like a private symbol in the army. Okay. Really easy for you, okay? This is the formula for a confidence interval for a population proportion, right? So we have P hat, so our sample proportion plus or minus our z-score times our, well, this looks like our standard error for the sample proportion, okay? Again, I gave you all of these z values for your confidence levels, okay? I wanted to make this as easy as I could for you. Again, z-scores are all standardized, so they're all figured out for you for these normal just for the normal populations, right? So again, we always want to assume normality if we can, okay? So these are all our z-scores, and then p hat is the sample proportion, n is the sample size, z star is the appropriate value from the standard normal distribution, and then for your desired confidence level, right? And also, I just want to say, this says by convention. What I assume that means is this 90% here, you're not going to get exactly a 90% confidence level. I think they just rounded it as close as they could to the closest z-score they could find that was the closest to 90%. That's what by convention means. As you can see, this one's 3 decimal spaces. The others are, we only deal with especially in the normal confidence table, we only deal with two decimal places, right? We have our tenths and our hundredths value places. So I assume that this is just like they couldn't find one specifically for the 90% confidence, so they just gave it a third decimal place to kind of make it a little bit more accurate. So that's all that means. Don't worry about it. It's gonna be fun. All right, so how to. I give you step-by-step instructions how to find a confidence interval for this population proportion, okay? Really easy, step-by-step. There's only 6 steps here, so if you are struggling, always refer back to this slide and the next one, okay? So step 1, determine the confidence level, find the appropriate z-value. Step 1, find the confidence level, find the appropriate z-value, okay? Step 2, find the sample proportion p hat by dividing the number of people in the sample, having the characteristic of interest by the sample size, right? So we take our p, I guess in this case it would be x, so x is our number of people in the sample, having the sample size divided by the population, okay? That's our p hat, what we call p hat. It should, again, note this result should always be a decimal value between 0 and 1, right? Just like we did in the last problem, that true proportion I think was 15%, that's 0.15. So we always have to have it between 0 and 1. Step 3, multiply p hat. So I guess multiply the chance of people having the characteristic by the chance that people don't have the characteristic, right? So p hat times 1 minus p hat, and then you divide by the sample size, okay? And then we take the square root of that from step 3, right? So this times this divided by this, and then you take the square root, okay? Multiply that answer from step 4 by your z-score, and then you can take p hat plus or minus the margin of error, okay? Which again is all of these steps, 3, 4, and 5. Good way to think about it is bracket it out. So separate the steps in terms of what goes together, right? So 3, 4, and 5, I'll deal with the margin of error. This is your p hat score, right? And then this is just like the total summation of all of the steps included in that one, right? So p hat plus or minus the margin of error, and you get your CI. Anyway, so here's an example, right? Let's just say you want to estimate the percentage of time within 95% confidence you're expected to get a red light at a certain intersection, okay? And suppose you take a random sample of 100 different trips through a certain light, through a certain intersection, and you find that you hit a red light 53 times out of 100. For me, it'd probably be closer to 90 times out of 100 because I don't hit any green lights. I hit every red light on my way here this morning, so not good luck for me. But anyway, we want to figure out our 95% confidence interval for this proportion. So what do? Step by step, here you go. You want to find a 95% confidence interval, so step 1 is you find your z-value. Again, our z-value is 1.96. Easy, we found it based on the table that I gave earlier, okay? Step 2 is we find our p hat, right? So we take our sample size divided by our population. 53 divided by 100, that's easy, 0.53. So p hat is 0.53. Next thing we do is we take p hat and we times it by 1 minus p, and then we divide it by our sample. This isn't our sample size, excuse me, let me go back a step. 53 is the number of times we hit the red light. So the number of times the characteristic being, characteristic that we're trying to find, right? How many red lights we hit, we take that number, and then we divide it by our sample. My apologies. Again, teachers aren't perfect. Okay, so chance of success, 0.53, times the chance of failure, divided by our sample size. Once we find this value, we take the square root of it to get our margin of error, okay? Once we do that, we can then take our z-score, multiply it by this number here, we get our margin of error, okay? Which is 0.0978 or 9.78%. And then again, if step 5, we take all that, add it together, okay? Or put all of it together, I should say. So that means that your 95% confidence interval for the percentage of times you will ever hit a red light at that particular intersection. We just do 0.53 plus or minus 0.0978. Again, that's just you take your chance of success, or the characteristic you're trying to study, and then you plus or minus it by the margin of error. And then of course this is rounded. They rounded it up to 0.10. I would never round it personally, just for accuracy's sake. I would leave it at 0.0978. That's a hefty round, right? That's almost, I think that's 22 decimal places, or 22 points or something like that. That's a lot. I wouldn't round it that much, okay? I would just leave it there. And again, this is a rounded interval, but you get my point, right? 0.53 minus 0.10, 0.53 plus 0.10. So we get, we can interpret these results within the context of the problem. You can say that, I can say that with 95% confidence, the percentage of times you should expect to hit a red light is between 43% and 63%. And this is just based on this one sample of 100 times, right? We could take another sample of 200 times and it may be different. We don't know, okay? But that's just kind of, and this is just kind of a simple example for you guys, step by step, how we do this, okay? So that's what we have for this. Look at there, we're done. This video is much shorter, right? I purposefully tried to give, it's a little bit less material, a little bit more complex. I hope I didn't confuse anybody. A little bit more complex, but a lot less material. I wanted to give that to you guys because I know you've been working hard, and I wanted to give you guys a little bit of a break today, so that way you can kind of not have to sit there for 3 hours, all right? So this week there's no real homework. I do want you guys to keep reviewing the videos, reviewing the material, reviewing the textbooks. Keep learning, keep asking questions. Again, here's another thing. Please ask questions. If you're confused about something, please ask me. I even put my email here. I promise if you email me, I'll get back with you within 24 hours. That's a guarantee, okay? You can ask Mrs. Bernardi as well. She can help you. She really does help you guys a lot with all of the problems and all of the practice examples and all that stuff. So she does a great job there. So please ask questions, okay? I want to answer them. I want to help you guys succeed, okay? Get ready, because next week there'll be another take-home quiz. So come ready to learn. I hope you're excited. I'm ready. I'm really excited. We're going to be diving into some more complex stuff. Again, we're kind of dying down towards the end of the semester, or end of the course rather. And so the material will be less and less, but it'll be a little bit more complex, because it's just building on all of the things we learned from the previous videos, okay? So come ready to learn, come ready to be focused. Other than that, have a great week. Spooky Halloween. Hope you guys enjoy Halloween. Don't steal kids' candy, or I don't know, don't steal my candy at least. I like it. But anyway, you guys are doing great. You're almost done. Session 5 down. We got 2 more to go, and then a final. You guys can do it. I believe in you, and have a great rest of your week. We'll see you guys later.